Welcome back. Today we will discuss an application of the quantum Fourier transform, that is the quantum phase estimation algorithm. We will first set the problem up, and then we will directly dive into it by applying a circuit that will do the job. Now the problem is that we have an unknown n-qubit unitary U that acts on an eigenstate in the following form. Essentially gives a phase of a certain eigenstate U, small u. And the quantum phase estimation tells us that if we can prepare the eigenstate U, we can estimate the phase phi to a m-bit precision. One of the ingredients that we require for the quantum phase estimation algorithm is an oracle, that is a control unitary that applies the unitary capital U only if the control qubit is in the one state. This is something that can be described by this following circuit, where we have n-bit word to encode the eigenstate U of the unitary capital U, and we apply it to an ancillary qubit in the state plus. Compared to before, the ancillary qubit now is the control of this unitary. When we do this, we see that the output state will be the state, the following state, where we have a coherent superposition of the ancillary qubit that is between 0 and 1 with a phase that depends on the unitary U. So we can repeat this operation n times, and what happens is that we will have a phase accumulation of small n times the phase of the unitary. Or another way to rewrite, a more compact way to rewrite this equation, is just as a sum in terms of the possible outcome of the ancillary state k0, and we can easily check that this phase will correspond to this state if k0 is equal to 0 or k0 is equal to 1. Throughout this module, then we will often use the shorthand notation for repeating this operation n times that is shown in this plot over here, where we just write down the matrix U to the power n. Now we can do the same and applying this oracle to m control qubits. Essentially, now we have a n-qubit registry that encodes the eigenstate U, and we have m control qubits that are all first Hadamard transformed. Now, what happens if we just look at the last qubit? It will acquire a phase to the power 0 phi. What will happen to the second qubit is that it will acquire a phase to the power 1 phi, and so on. And the last qubit will have a phase to the power m minus 1 phi. Or, in other words, we can combine all of this just by saying that the final state will be just the sum over all possible control qubit in the all possible to the power m control qubit and control code words k, just with a phase shift that depends on k and phi. We will often use the shorthand notation for this circuit that look like this. Now we're in the position of doing something useful with it. And to do so, we will apply an inverse quantum Fourier transform to the control lines. Now I remind you that the inverse quantum Fourier transform is essentially the reverse map that takes as an input this combination of state and maps it back into the state J. If we take a look at this input state, then it's easy to see that the output state will be just a very simple one, where we have as an output just an approximation, an m-bit approximation of the phase of the unitary transformation that we wanted to estimate the phase of. Now, in summary, we now seen that we can estimate the phase of a unitary to an arbitrary precision. And this is actually, this quantum phase estimation algorithm is a key subroutine in many quantum algorithms, most notably in Shor's algorithm that we will be discussing next.